can a machine be creative? There is no easy answer, and we as humans have been searching for one for more than a few years. What we do know is that machines can create. They produce incredibly realistic illustrations, texts, and music, generate faces and voices, and are so advanced that they compete with humans to see which can get the best result. In recent years, generative AI models like ChatGPT, Midjourney, DALL-E, Adobe Firefly, and Bard have made fantastic progress in imitating how we humans handle creative tasks. So, let's take off the wraps and explain what's inside the mind of an AI artist or writer. By generative AI, we mean machine learning algorithms that can be used to create new content from existing content. The core idea is to generate content that will be indistinguishable from what a human might produce. Why do that at all? Why do we need machines to learn that? The short answer is automation. This is simply a new step towards better efficiency, saving time and resources while freeing people from repetitive tasks. There is certainly demand for more content in industries such as e-commerce, marketing, and media, and AI can assist humans in producing good results more consistently and in a shorter time. And today, with generative AI inescapably immersed in our private lives and businesses, we've also discovered that AI content can help us in research, planning, creative brainstorming, and a myriad of other situations. Of course, one of the reasons for generative AI development is curiosity. Humans have long been fascinated with the idea of automated art. Maillard's automaton, for example, built by a Swiss mechanician in the 1800s, was capable of writing poems and drawing pictures from its very short mechanical memory. Philosophers, science fiction writers, Hollywood, and video game developers have often shown the art created by AI as an illustration of a machine's humanity, the last bridge towards total consciousness. Yet, as it turned out in recent years for machines, making art has little to do with consciousness, just a lot of data preparation, training, calculations, and many fantastic human minds developing the technology. Let's talk about what fuels the most popular generative AI tools that you've been using, and we'll start with image generation. The first technology that allowed us to receive those fascinatingly realistic images is called Generative Adversarial Networks, or GANs. Like many breakthrough inventions, GANs were ideated in a bar over a beer. Ian Goodfellow, a computer scientist who came to a Montreal bar to celebrate his friend's graduation, got involved into a discussion on building a machine that could create images by itself. Right there, an idea struck him. What if two neural networks were pitted against one another? That same night, he coded his system and it worked the first time. In 2014, he and his team published his paper, and since then, the world has never been the same. Goodfellow himself continued his career working at Google, OpenAI, Apple, and now at DeepMind, one of the most innovative AI research companies in the world. Before we talk about the magic of how GANs work, let's introduce you to deep learning and neural networks. Deep learning has become the most revolutionary technique in AI development, the one responsible for the advancements in image and speech recognition, translation, and, of course, content generation. And it does that by utilizing neural networks. The idea of artificial neural networks was inspired by the neural connections in human brains, the ones that help us learn about the world. In the same manner, neural networks allow machines to recognize patterns from data, make predictions, and see hidden relations. Just as human brains receive signals about the world, artificial neural networks receive data. After passing this data through many of its layers, the network can make a prediction about what that data is. But to be able to recognize, say, that there's a human depicted in a photo, a neural network must first be trained on many images of human faces. There's a more detailed explanation of deep learning in our video on computer vision, so be sure to check it out. So, what did Ian Goodfellow's breakthrough idea mean? How and why would you pit two neural networks against one another? GANs consist of two competing neural networks. One, a generator, creates fake examples, and another one, a discriminator, tries to determine whether the sample is real or not. That's where the name of this technique, generative adversarial networks, comes from. A generator is like a learning artist trying to copy a famous painting, and a discriminator is an art expert in training who must determine if it's a copy or the original. A discriminator is trained on both fake data from the generator and real data, which are labeled as such. In the beginning, the mechanical artist doesn't produce a convincing result, but with each iteration, the network improves its performance. When a generator is finally able to fool a discriminator and a human, the process is considered a success. Whichever network is the winner, it remains the same, while the loser is updated again and again after each feedback loop. The GAN architecture has been used in many AI image applications. It was the first technology that fooled us into believing that these were real humans. The one that powered FaceApp, which went viral a few years ago for realistic aging filters, and the one we've been using for transferring renowned artists' art styles on our personal photos. Some younger AI tools, such as Jasper Art, also rely on GANs to generate images or change the style of the image. But over the last couple of years, a different generative method has emerged to become the standard practice for such tools as Stable Diffusion and the latest versions of DALL-E. It's called the diffusion model. The first diffusion model was invented in 2015 by Yasha Sol-Dickstein when he was exploring non-equilibrium thermodynamics at Stanford. Now, he's a principal scientist at DeepMind. What's the connection between thermodynamics and AI? Diffusion, by itself, is a physics principle that can be demonstrated, say, by spraying some perfume in a room. At first, the fragrance molecules are concentrated in one area, but they will soon spread across the space, becoming dispersed. Non-equilibrium thermodynamics describes the probability of finding a fragrance molecule in the room at each step in the diffusion process. Sol-Dickstein's idea for generative modeling was to turn images into noise, like dispersing perfume in the room, and then teach the system to reverse the process and turn the noise back into images. To help this make more sense, imagine you're trying to prepare a meal from your childhood. You don't have the recipe, you don't even know what it's called, but you vaguely remember the taste. So you decide to gather a few ingredients that might have been present in the original meal and prepare them together. You try the finished version and realize that something isn't right. So you tweak some things here and there and try it again. You tweak and you try it once more and again until you're pretty confident that you've got everything right. Now you know the recipe. In image generation, the process is similar. First, diffusion models take an image from the training set and successively add noise to it, just like our childhood memories get blurrier with time. At each step of the process, the model learns what the image looks like with different levels of noise, empowering it to reverse the process. Then, the model tries to reconstruct the image from the noise by trying to predict the less noisy picture that came a step earlier. The result will be wrong at first, so you tweak the parameters until the model works better. And finally, the model shapes the noise into a new image. Diffusion models are exceptionally good at generating not only realistic images, but also music and sound effects from text descriptions. Are they better than GANs at this task? Both methods succeed at creating detailed visual samples, but there's research favoring diffusion models. Yes, due to multiple denoising steps, diffusion models are slower than GANs, but they can also create more detailed images thanks to their ability to first work through the rough sketch and add fine details on top of it. Diffusion models have also been used to accomplish additional tasks, such as filling in marked areas with something based on a prompt or extending the image beyond its borders. The features employed by image editing software like Canva and Photoshop are powered by OpenAI's DALL-E and Adobe's own Firefly Generative AI. But how exactly do AI generators understand text prompts? Machines don't speak human languages after all. This is where natural language processing comes into play. NLP is a branch of AI tasked with giving computers the ability to understand human speech the same way we do. And this is done by translating the request into something the machine understands. Numbers. How can a word become a number? Well, you can create a vocabulary and assign every word in your dataset a specific number, but that won't capture the relationships between those words. It won't capture any context, so it makes sense to use word embeddings. Word embeddings are vector representations of a particular word. Vectors act as coordinates in the space, dictating where to place words based on their unique features. The closer the words' meanings are, the closer their vectors are. So, when you write a prompt into an image generator, the model encodes each word from the prompt into a numerical vector format, capturing their attributes and the relationships between them. This way, the model knows how to illustrate those concepts together. The model is trained on pairs of images and their corresponding descriptions, so when you show it a new image, it can very accurately label it with a correct description. Natural language processing is also the field where text generators operate. It's clear how they understand us, but how do they write coherent text? OpenAI's ChatGPT and Google's Bard are examples of language models that can understand and generate human language. To be more exact, they are chatbots powered by such language models as GPT-3, GPT-4, and Palm 2. They can answer questions, translate text, solve math problems, write code, and perform advanced reasoning, all while understanding the nuances and intricacies of human speech, being able to fool anyone into thinking that they're talking to a real human. The foundational architecture behind ChatGPT is hidden in its name. GPT stands for Generative Pre-trained Transformers. The transformer architecture was developed in 2017 by Google employees and led to the creation of a large language model like BERT. In 2018, OpenAI improved upon the idea by introducing GPT-1. Pre-training meant that the model was first trained using unlabeled data to learn general patterns and the relationships in it, and only after that was fine-tuned with a smaller labeled dataset specific to the task at hand. To put it very simply, since we don't want to bore you with tons of technical details, transformers can predict what the next word in a sentence might be. They do so by employing a self-attention mechanism. This mechanism can look at each word with respect to all other words and calculate how much attention each word must pay to every other word in a sentence. This way, the model can understand the context and relationships between the words. You know how it works when you're reading a book in a language that you're not native in. You might encounter unfamiliar words, but through your experience you will likely understand if it's an adjective or a verb, if it's singular or plural, and what word is likely to follow to ultimately guess the meaning. It's about context. Today's state-of-the-art language models are powered by transformers, and they're getting better all the time. The latest from OpenAI, GPT-4, is 10 times more advanced than its predecessor. It can understand nuances even better, including pinpointing emotion in the user's text and using dialects. It also cites sources, solves more complex scientific problems, generates extraordinary coding results, and understands what's depicted on graphs and images. Perhaps by the time you're watching this video, a new, even more revolutionary version has emerged. The power of AI is only as big as the context humans are providing it. Depending on the input, AI can either generate a brilliant idea or a mess of shapes with some realistic visuals. The hybrid of human-machine interaction is what brings out the true excellence in AI. Regardless, generative AI is here to stay. At times controversial, sometimes worrying, often misunderstood, AI-generated content is a fascinating scientific achievement that might change the world like the Industrial Revolution or the invention of the Internet did. If you want to dive deeper into the many possibilities of employing generative AI in work and business, there's a separate video waiting for you on our channel. Also, subscribe if you want more content on the topic, and leave us a comment if you have any questions about generative AI you want answered. We will see you in the next videos where we dive deeper into the inner workings of generative AI.